Imagine this is 3 a.m. and your pagers goes off. Your entire production cluster is down. Why? Because the one machine running your control plane just died. No API access, no access to deployment, a total panic. Today we are going to make sure that that's never happened to you. We are talking high availability. By end of this video, you will understand the math behind the etcd quorum, why 2 is the worst number in Kubernetes, and how to design a cluster that is practically unkillable. This is actually a free lesson directly from my full Certified Kubernetes Administrator Mastery course. If you want to go beyond the theory and actually build the cluster step by step with me, but for now, let's eliminate the single point of failure.
Hello and welcome back. In previous topic, we identified the specific component that make up Kubernetes control plane and etc worker nodes. We saw the components like the kube API server and etcd are absolutely critical for the cluster to function. This leads to a very important question. What happens if a single machine running in your control plane fail? If that node goes down, etcd is gone. The API server is unreachable and the controller stop running. While your existing application on the worker nodes might continue to run for a while, the cluster is effectively dead. You cannot deploy any application, scale existing ones, or respond to any failure. Your cluster is no longer available. This is what we call a single point of failure. And in any production system, our goal is eliminating them. The solution is high availability or HA. HA is a practice of designing a system to be resilient to failure. Ensure it remains operational even when individual components fail. When we when we talk about Kubernetes HA, we must start with its brain and source of truth, etcd. Making etcd highly available is the fundamental foundation of a resilient control plane. etcd is distributed system, meaning you can run it as a cluster multiple member. For this cluster to work, it needs to be able to safely write data and agree on the state of the world. So to do this, it needs to achieve quorum. Quorum is a minimum number of members that must be online, an agreement for the etcd cluster to operational. The formula for quorum is n over 2 plus 1, where the n is the total number of the member. The formula is the exact reason why you will always hear the advice. Always run at odd number of control plane nodes. Let's see why. Imagine a two-node etcd cluster. To have the quorum, you need to divide like 2 over 2 plus 1, which means 2. This means both members must be online. If you lose one, you lose quorum. And a two-node cluster has zero fault tolerance. Now let's look at the three-node cluster. Quorum is like 3 over 2 plus 1, which round down to 2. This means you can lose one member and the remaining two still form a quorum and keep the cluster operational. A three-node cluster has a fault tolerance of 1. What about four-node cluster? Like we can use the quorum, like 4 over 2 plus 1, which is 3, means that you can still only afford to lose one node. If you lose 2, the two remaining number can form a quorum. So a 4-node cluster has the same fault tolerance as a 3-node cluster, but with more overhead, of course. This pattern continue. A 5 cluster node can tolerate 2 failure, while a 6 node cluster can also only tolerate 2 failure. So the odd number always give you the best return of fault tolerance for the number of the machine you're running. That's why production cluster will almost always have 3 or 5 control planes. Now that we know that we need to multiple etcd member, where to run them. This leads to a two common HA architecture. In the first is the stacked control plane. This is the most common approach where the etcd members run the same machine as the other control plane components, like the Kube API server. It's a simpler to set up and require fewer machine. The second architecture is using external etcd. In this model, you run your etcd cluster on a dedicated set of machine, completely separated from the nodes running the Kube API server, scheduler, and controller manager. Why would you like to do this? It's uh, it's provide a better high availability by decoupling the component. If a control plane node running the API server fail, it doesn't also take down a etcd member with it. This separation can be crucial for very large scale or business critical cluster where maximum resilience is the goal. Okay, so we have three control plane nodes, each running its Kube API server. This is a great redundancy, but it creates a new problem. How do all the worker nodes and your kubectl client know which API server to talk to? Do you have to keep list and switch manually if one fail? Absolutely not. This solution is to place a load balancer in front of your control plane node. The load balancer provides a single stable IP address or DNS name that can act as front door for your entire cluster. All components, from the kubelet on the worker nodes to your own command line, are configured to talk to this one address. The load balancer job is to distribute the incoming traffic across all healthy Kube API server instances. It's constantly run health check. And if one of your control plane nodes fail, the load balancer will automatically detect this and stop sending traffic to it. Seamlessly redirecting all requests to the remaining healthy node, this is essential for automating the failover. A resilient control plane is the most important setup, but true high availability involves the entire cluster. You need to think about resilience at every layer. First, worker nodes and workload. Don't just move worker nodes. They run them in a different physical location. In cloud, this means that distributing your worker node across multiple availability zones or AZs. AZs are essentially a separate data center. If a whole data center goes offline due to power outage, network failure, your cluster can continue running on the node in the other AZs. The to complement this, you should use Kubernetes feature like pod anti-affinity. This allows you to create a role that tell the scheduler never place two replicas on my application on the same node or even the same availability zone. This prevent a single point of failure at both the node and AZ level of your application. Next is storage. If your application needs to store data, that data must be highly available. You should use resilient network storage solution that replicate the data. In the cloud, this means that using storage classes that are multi-AZ aware. So if a pod fails or the new AZ, the storage volume can follow it. Finally, networking. For on-premise cluster, this means that having redundant switch and network path. In the cloud, you can largely rely on high available networking infrastructure provided by your cloud provider vendor. It's it.
And there you have it. Now you know why we use load balancers and why we always run odd numbers of etcd nodes. Seriously, don't run the two nodes. The math doesn't work. But here's the catch. The CK exam is not a multiple choice test. You can't just know this theory. You have to build it. You need to know how to stack the control planes, how to back up the etcd, and how to fix it when it breaks. This is exactly what we do in full Kubernetes mastery course. We take this theory and we get our hand dirty in the lab. If you want to stop guessing and start mastering Kubernetes, click the link below. I'll see you in cluster. Cheers.